Hi. So in the previous lecture, we saw geometric join of simplicial complexes, and today we are going to see simplicial the join operation for topological spaces. Okay. So let's just recall how we defined the join for spaces as we took the Cartesian product of the spaces along with the interval 0, 1 and then mod it out with shrinking entire x on the end, let's say 0, and y on the end 1. This is how we took the join of spaces. And now we see how we can do a geometric join. Okay. So for two subspaces x and y of Rk, suppose there are some spaces u and v which are skew affine such that they sit inside some big enough Rn, and skew affine means that their intersection is empty and their affine hull is having dimension u plus dimension v plus 1. That is, it is full dimension. Okay. So there is no redundancy when you take the affine hull of u and v. So if you have such a space u and v for your spaces x and y, and x and y are bounded, we define their geometric join as, so this is the notation we are using, x geometric join y to be the collection of all the points of this form. You take a point from x, you take a point from y, and put the line joining the point x with y. Okay, so this is a set in Rn. This set is defined as the geometric join of x and y. Okay, so you should check that if you have spaces that are bounded and are sitting inside some skew affine subspaces u and v of Rn, then their geometric join and their usual join, which we defined as x cross y cross 0, 1, mod it out with x identified to a point at 0 and y identified to a point at 1. These both definitions give you homeomorphic spaces. Okay, and then using this, now we come back to the original question which we posed in the last lecture, that if you have K and L which are simplicial complexes, then whether you take their geometric realizations and then take the join, or you take their join first as simplicial complexes and then take their geometric realization, these spaces are homeomorphic. And using this, now you can see that if you have two spaces that are homeomorphic to each other or even homotopic to each other, then their geometric joins gives you that it is preserved under the join. Okay, so if K is let's say homotopic to some K prime, L is homotopic to some L prime, then K star L is going to be homotopic to K prime star L prime. Okay, you take homeomorphic, not homotopic. So and here I'm using some abuse of notation when I'm doing when I'm writing this, I'm actually meaning the geometric join for these spaces, because now I have come down to geometric mean. And also one should be able to see very clearly that if you take x, so since all these definitions are equivalent, they are going to give us homeomorphic spaces, we just denote it by x asterisk sign. Okay, so the space x join y is homeomorphic to y join x, and also it is associative, that whether you take join of two spaces and then take it with another, it does not matter in which order you take their joins. Now next construction which we have are of the cone and suspension. What you really do is, in the cone construction, you take join of a space with a single point. Okay, so to see it very in a nicer way, look here. So all you are doing is that you're taking a point P at some which is away from X, okay, like completely disjoint from X. And then if X, let's say, is just a line like this, so if X is a line like this and P is some point here, then you put all these points. Okay, so my lines are going out of frame, but this is what you really do. Okay, all of these lines are there this way. Yeah. And also, if you want to see it as the other definition, you can see it as x cross 0, 1, and you identify the points of x at one point, either at 0 or at 1, doesn't really matter. So this is a cone over x. These definitions are equivalent, you can check. Other one is the suspension construction, which is similar to cone's construction, only difference being that here we took join of x with 1 point. In the suspension, we take the join of x with 2 points. So it's more or less like you have an x here, there is an x here, there is a point, let's say some x, let's say z, and there is some other z prime. And now from this, you do the entire cone construction on X. And from this also, you do the entire cone construction on X. Okay. And you, of course, fill in all of these possible lines. So this is your suspension. This again can be seen as you take the X, space X, you product it with the interval 0, 1, and then all the points lying on the level 0, which are x comma 0, are identified to 1 point. Let's say this particular point here. Okay, this point here is the x cross 0 identified to a point, and this point here is the x cross 1 identified to 1 point. So this is how we do the suspension construction over a space X. Yeah. Now moving forward, there are a few notations. So points of x join y will be written as tx direct sum in some sense, 1 minus dy. Why do we really write it in this sense? Because which x is being chosen at the t equal to 0 is irrelevant because it will vanish. And similarly, what point is chosen at t equal to 1 from y is irrelevant. So it's actually in some sense a direct sum. And similarly, now then you can have the notation for the n-fold join to be t1 x1 direct sum, t2 x2 direct sum, t3 x3 and so on till the tn xn, such that all these ti's sum up to 1 and these xi's are coming from the space x. So this is n-fold join of the space x, and this is how the points of the space are denoted. So note that if you have this notation, the x join y as a space is not equal to y join x. We know that they are homeomorphic as spaces, but they are not equal. Okay. And also, we can see that when you want to define the x join y and you want to compare it to the Cartesian product, you can always embed a Cartesian product copy of x cross y into the x join y at any t which is not 0 and 1, right? So this you should be able to see from any of these definitions. You take any x cross y and a t not equal to 0, and there is a copy of x cross y there. Yeah. So this way one can see that there are plenty of x cross y sitting in x join y. And once you have the join of spaces, how can we extend the maps from spaces to the join of spaces? For that, let's see if we have a map f from x to y, g from u to v, and we consider the join of x and u, which is this, and another space y join v, which is this. I can actually define a map f join g from this space to this space in the most obvious way, that any point here. So with this notation, I know that points of x join u look like dx. Okay, this should have been a direct sum plus, but since this is how we're going to write, I can skip it. So this is tx plus 1 minus tu, and it should be sent to t of fx direct sum 1 minus t of gu. Yeah. So this way we can define join of maps. Now, another important term in topology is about the connectivity. So we all know about the connectedness of a space, whether it is path connected, simply connected, etc. What are the higher analogs? So of course we can't keep on giving names. So what we do is we define it in terms of the highest possible index up till which the homotopy groups vanish. So intuitively what it really means is that the space we call is K connected if there is no hole up till that dimension. So this might remind you of the K dimensional holes in homology, right? There we in some sense say that, okay, if you're able to move a sphere around freely, then you say that there is no hole of that dimension, otherwise there is a hole. Here we say it in a little different way, that if you have any SI which can be shrink to a point, okay, if each SI can be shrink to a point, then we say that there is no I-dimensional hole in the space. Okay, so if there is even one SI, one or rather one SK, k-dimensional sphere, which cannot be shrinked to a point staying inside that space, then we say that the space X has a k-dimensional hole. Okay, so pictorially what it really looks like, that if I take this disk cutout, then and I consider this thick line as my S1, then this is a one-dimensional sphere which cannot be shrunk to a point because there is a hole here. Okay, so I know that X is not one connected. Why? Because there is an S1 which cannot be shrinked. And a formal mathematical definition tells us that for a k greater than equal to -1, we will see why we are going all the way till -1. That's for some notational purpose. For k greater than equal to -1, a space is k connected if every continuous map f from SL to X is null homotopic, where L is anything starting from -1 up till k. Okay, so having k connected means that all the maps, all the continuous maps from S minus 1 to X, S0 to X, X1 to X, so on up till Sk to X, all of these are non-homotopic, which means they are homotopic to a constant map. And constant map is precisely a map which is giving you a point. Okay, so you're saying that if f can be or rather if this SL, the image of this SL via F in X can be shrunk to a point or not, is what we are examining here. So coming to the K equal to -1, so notice that S of -1 is nothing as we know so far. S0 is a disjoint collection of 2 points. S -1 by notation is fixed to be the empty set. Okay. And B0 is a singleton point. So X being -1 connected means by notation that X is non-empty. And then connectivity of a space X is defined to be the highest number K such that X is K connected. Okay. Now we'll see a very well-known result that Sn is n-1 connected, or rather connectivity of Sn is n-1. Okay. So everybody knows that Sn cannot have connectivity n. Why? Because if you consider the antipodal map F from Sn to Sn, the 2B version of Borsuk-Ulam theorem tells us that there is no map F from Bn to Sn which is antipodal on the boundary of Pn, right? Which means this map F from Sn to Sn cannot be extended to a map from Bn to Sn. So this extension version is equivalent to saying that the map is null homotopic, right? Therefore, I know that the connectivity of Sn is not equal to n. Therefore, connectivity has to be lesser than n. We are examining the maximum possible case such that X is K connected. I know that X is not n connected, therefore the maximum has to be less than n. So connectivity is less than n. For this, let us take an F from Sk to Sn, assume it to be a uniformly continuous map. Okay. And we do this for any k which is less than n. What we really want to show, we want to show that F is null homotopic. And to show that, what we do is that we construct a map G from Sk to Sn, which is homotopic to the original map F we started off with. Furthermore, image of G is not the whole of Sn. And once I know that the image of G is not whole of Sn, which means there is a point which the image of G misses out. Let's say some alpha. So there is some alpha in Sn such that alpha does not belong to image of G. Now, if alpha does not belong to image of G, and assumingly if minus alpha belongs to image of G, okay, then the entire image of G can be shrunk down to minus alpha, right? And therefore G image, rather the map G will be null homotopic. If you say that, oh, there is no such point, there's going to be some point which it misses out. And then you choose a point which is different from it, but it is in the image, and then you shrink the entire image of G to that point. And this way you will get that G is null homotopic. Now the work starts for constructing such a map G, right? So this G we will actually construct through a homotopy so that we don't have to sit and define the homotopy between F and G. We start with a homotopy which does the job for us. Okay, but for that, let us first, since we started with F to be a uniformly continuous, okay, I haven't written. So F is uniformly continuous map. Therefore, choose an epsilon such that whenever distance between any two points x and y is less than epsilon, distance between fx and fy is less than 1. Okay. Also, choose a triangulation delta of Sk such that for any sigma in delta, the dimension of delta is less than 1, less than epsilon. Okay. Now we define the map F, which we claim to be the homotopy between the F and the to be defined map G. How we define it is taking any point x from xk and t from the interval 0, 1, define f of xt to be the norm 1 element t summation lambda I fbi plus 1 minus the fx. Where the summation is running over, we will see now. So first of all, recall that if you take any point x, which is in the geometric realization of a simplicial complex k, then there is a unique simplex in k whose relative interior contains the point x. Excuse me. So pick that particular simplex of k whose relative interior has the point x and call it support of x. Okay, then support of x being a simplex has its vertices. So vi are the vertices of this support. So let's say v1, v2, vm are the vertices of the support of x. Then for f of xt, the summation runs from I starting from 1 to n. Okay, this denominator is nothing but just to make it a norm 1 vector. Okay, so nothing much is happening here as of now. All you care about is that since you want the image to land in Sn, you have to divide it by its norm to make it a norm 1 element. Of course, provided that this is non-zero. Okay, and that is going to be the next task now. And yeah, so the vertices of support x are the vertices v1, v2, vm, and writing x as the linear convex combination of these points vi's in this fashion. Okay, so with this, now we understand what the map fxt is. So it's actually perturbing the function f a little bit using the support of x and defining the values locally there for the f. Okay, and that's precisely what we want to do to achieve the function g. But before that, we have to say that why this is indeed a homotopy. We just know that as of now it is some map. It may not even be a well-defined map. So see all that. To see all that, we need to show that this denominator does not vanish. And once we know that this does not vanish, these being all continuous maps and other being the linear combinations will tell us that this entire function is going to be well defined as well as continuous. So to show that f is a homotopy, we need to show that the denominator is non-zero. Now notice that since the condition we have put on the triangulation is that whenever the points are at a distance of epsilon, their images are at a distance less than 1. And we have chosen the triangulation to be such that the diameter is less than epsilon. Therefore, given any simplex, the points which lie in the same simplex cannot be farther than epsilon, right? So you come here and see that then since any two vi's or even the x, so x lies in the convex hull of these vi's, right? This is the this is the reason. X lies in the convex hull of VIs, and no VIs are, and the diameter of this support X is less than epsilon. Therefore, each of these VIs and X are at a distance of less than epsilon from each other, and thus their images FVIs and FX are at most at a distance of 1 from F1, and thus they all lie in a spherical cap which has radius less than 1. So it's not even a full hemisphere, okay? It is some lesser portion, some strictly above the hemisphere. You put a hyperplane which is little off the origin. So what it really says is that the convex hull of these points, f of vi's and f of x, it is going to exclude the origin. Therefore, f is well defined, right? So this is nothing but the convex hull of all these points, right? So therefore, this entire point is not hitting the origin, and hence this is non-zero, and therefore this entire thing is in Sn, and its continuity now anyway follows. Therefore, F is a homotopy. It's a well-defined continuous map, defines a homotopy from F to a point, to another map. Why it is F? Notice that at t equal to 0, this first term vanish in both numerator and denominator, and here you just have fx upon norm of fx. But notice that f is already a map from sk to Sn. Therefore, f of x already has norm 1. Therefore, norm of fx is 1. Thus, you are left with just fx. So, f of x comma 0 is fx. Therefore, we have the starting of this family of functions to be f. We define the f at the other end to be the g. So capital F restricted to sk cross 1 is the map g. Now, since the diameter of sigma is less than n, image of sigma is contained in a hyperplane in Rn plus 1 passing through origin. Yeah, but there are finitely many simplices in the delta. Therefore, when you take the image of G of Sk, you are going to get finite union of such hyperplanes. And finite union of such hyperplanes cannot cover the whole of Sn. Therefore, the map G, which we have defined in this fashion, is not a surjective map, and hence it will miss out a point. And as I have already described above, that for such a map, you can see that the G is null homotopic. Therefore, and since F is homotopic to G, F also is null homotopic, and thus any map any map F from Sk to Sn is null homotopic. Therefore, the connectivity of Sn is exactly n minus 1. So today I'm ending here itself. It's a very short lecture. In the next talk, we will see there are few ways how we can show some spaces k connected or compute its connectivity, and we'll see like similar tools for the computations in similar simplicial complexes, cell complexes, because to work in general topological spaces it is quite hard, but things are comparatively easier when we work with simplicial complexes, especially in topological combinatorics. People are almost always interested in finding the homotopy type of certain spaces, and that too, it's more or less always about saying the homotopy type of so and so space is a wedge of spheres, or it is a wedge of equidimensional spheres. And for all those, we need uh, like some of these techniques are really useful. So yeah, we'll see a collection of techniques in the next talk.